Hi everyone, I'm Suman Kumar, the founder of DWaste, a researcher, author, and a green software practitioner. At DWaste, we are building an AI-powered platform that helps schools and educational institutions measure and support their waste reduction initiatives. In today's presentation, I will walk you through the practical steps we take here at DWaste to minimize the carbon footprints of our AI models. Let's start from the AI and its carbon cost. From the first computers to today's AI, technology has come a long way. Early machines could only follow strict rules, but now AI can learn, understand, and even create. The timeline of notable AI systems is shown here, where we can see the first programmable electronic computer, ENIAC, which was built in 1945. In the mid 2010s, AI system achieved human comparable performance in specific language and image recognition tasks. This shift from rule-based systems to learning systems is changing how we interact with technology every day. As training computation has increased, AI systems have become powerful enough to generate entirely imaginary content that matches or even surpasses the realism of real world. As soon as here, we have seen the progression, but at how much competition? Modern AI systems rely on immense computational power to produce better results. This computation is measured in floating point operations per second, flops. Insert flops. A flop is a basic arithmetic operation such as addition, subtraction, multiplication, or division performed on decimal numbers. And the training compute refers to the total number of flops required to train an AI model. The diagram illustrates various AI systems grouped and color-coded with the computation required for training it. As we can see, these demands have now reached tens of billions of petaflops. Moreover, the amount of training compute has been doubling approximately every 6 months, a pace that far exceeds even Moore's law. Now, let's look into the amount of carbon emissions from training an AI model. The energy demands of modern AI carry a significant environmental cost. For perspective, the CO2 emissions from training common natural language processing (NLP) model can exceed the lifetime emissions of 5 average US cars, 17 years of an average American's carbon footprint, 17 years of an average American's carbon footprint, or the emissions from more than 300 plus air flight from New York City to San Francisco. This single comparison highlights the substantial carbon footprints of an AI training, and with countless AI systems in operation worldwide, this impact multiplies rapidly. Now, let's examine the projections of electricity consumptions and carbon footprints in AI. Current forecasts indicate that by 2027, AI will consume over 2% of global electricity and is already responsible for more than 10% of data center power. Without deliberate intervention, this carbon footprint is set to grow exponentially. So, how can we build AI systems with low carbon emissions? To illustrate, let's example how the DWaste platform implements greener AI practices. DWaste is an AI-powered platform that provides real-time sorting guidance and data insights, helping schools and institutions reduce waste. Our mission is to support waste reduction initiatives and combat recycling contamination using AI-driven insights and guidance. We actually contribute to Sustainable Development Goal 9, which is industry, innovation, and infrastructure, by deploying AI solutions that modernize recycling infrastructure and enhance resource efficiency, aligning with targets 9.4 and 9.5. Our efforts also support SDG 12, which is responsible consumption and production, and by improving recycling effectiveness, reducing waste generation 12.5, and advancing environmentally sound waste management, which is 12.4. Through this work, we help industries and communities transition towards a more sustainable and resource efficient future. Let's say DWaste in action.
Educational institutions are stepping up for sustainability, but without real data, how do you know what's working? From campuses to classrooms, institutions launch waste reduction initiatives, but most rely on guesswork. There's no consistent way to detect waste types, enforce sorting rules, or track progress. DWaste changes that. It's a mobile app powered by AI that instantly detects waste and tells you how to dispose of it based on your institution's own waste management rules. As users scan and sort correctly, they earn points. leaderboards let classes, dorms, or campuses compete to be the most sustainable. Want to automate waste tracking across your institution? The optional DWaste Edge device installs near bins to capture images and classify waste automatically. No phones or manual work required. DWaste helps institutions reduce waste, meet sustainability goals, and turn data into powerful learning and policy tools, while engaging students in meaningful, gamified climate action. Ready to build a cleaner, smarter campus? Start your journey with DWaste today.
Our core principles for low carbon intelligence are engineered to minimize DWaste environmental footprints across our entire operation. We adopt an edge-first architecture, processing data directly on user devices to eliminate the energy waste of idle cloud servers. We measure operational emissions of our AI models using tools like Core Carbon to track CO2 emissions as a key performance indicator alongside with accuracy and with a focus on green software practices. Our systems are built with efficiency by design, optimizing models and matching them to efficient hardware accelerators in line with model optimization best practices. Finally, we leverage rather than rebuild, using approaches like transfer learning and always stopping to avoid wasteful computation from scratch. Together, these principles ensures our AI is responsible as well as it's powerful. Let's look into the measurement part. We have integrated core carbon directly into our pipeline to track emissions. The formula for calculating emissions with core carbon is shown here. It accounts for hardware energy consumptions, which is measured in kilowatt per hour, and multiplies it by the regional carbon intensity of the electricity grid for the duration of the computation. Since our work involves image processing and deep learning, we use dual Tesla GPUs located on Iowa's electrical grid. If you look at the Iowa's grid comparison, which is shown here, reflects a mix of renewable and non-renewable sources. We measure emissions across key life cycle stages, which are data preparation, model training, and single inference call. This level of transparency ensures accountability, as we firmly believe you cannot reduce what you don't measure. Now let's examine the model selection and the operational carbon emissions by lifecycle stage. For this purpose, we rigorously tested state-of-the-art architectures for waste classification and detections, including EfficientNet V2, MobileNet, ResNet, YOLO V8 and V11, and a custom YOLO V8 CBAM model. Our evaluation extends beyond the standard metrics such as accuracy, F1, and mean average precision to also assess VRAM usage, model size, and carbon emissions. A key finding from the experiment was that for classification tasks, emission from ongoing inference often surpasses those generated during initial training. These insights directly informs our approach. We select models that maximizes accuracy while minimizing carbon emissions. Now let's explore the steps we took to optimize these models further. For this, we fine-tuned pre-trained models using a transfer learning approach, which offers greater efficiency and performance than training from scratch. For instance, our YOLO V8 CBAM transfer learning model achieved nearly 81% F1 score, representing a 21.4% improvement. This came with remarkable efficiency. The best fine-tuned models required comparable training time, but with a drastically lower carbon footprint. Our YOLO V8 transfer learning model, for example, also emitted only 0.014 kg carbon CO2, demonstrating that transfer learning is not only a shortcut to better performance, but also a greener one. Now let's explore how to deploy optimized models on edge devices. Full precision models store their weights and computation in 32-bit floating point format, making them large and storage intensive. To optimize them, we reduce their numerical precision by converting from 32-bit to 8-bit. This reduction enables processors to execute more operations per second, significantly boosting computational efficiency. This process is called quantization, a key optimization technique that enables AI models to do more with less. By reducing numerical precision, we shrink the model's footprint without compromising its intelligence. For DWaste, this yielded compelling results. Model size decreased from 42 to 76%, Inference speed also is increased by 5.2 times on average. We also achieved over 99% accuracy of the original accuracy while maintaining stable, predictable memory usage. These gains make quantization essential, enabling efficient and responsive deployment on edge devices where power and computational resources are limited. Our quantized models are deployed to apps and edge devices, processing data directly on local hardware such as tablets, phones, or on-site devices instead of running it in energy-intensive cloud data centers. This approach is greener for three reasons. First one is it eliminates the idle waste of underutilized cloud servers. Second one is amortize the embodied carbon of manufacturing fewer centralized servers, and the third one is it reduces the energy needed for constant data transfer. These efficiency gains directly support the real-time on-site requirements of DWaste. Beyond its sustainability benefits, edge deployment also delivers crucial operational advantages, including offline functionality, low latency, real-time processing, and enhanced data privacy. Now let's explore some of the strategies for making an AI project greener. These strategies are built on dual foundation. One is infrastructure and operation, and the second one is development and modeling. On the infrastructure side, we prioritize greener efficiency through spatial shifting, temporal shifting, and hardware efficiency. In development, we focus on selecting the right model for the tasks, integrating carbon-aware measurement tools like Code Carbon and Ecologist, and applying efficient training techniques such as early stopping, parameter optimization, pruning, and post-training quantization. Together, these strategies ensure that every AI project is powerful, practical, and carbon conscious. In the broader mission of AI for climate solutions, it is essential to choose purposeful intelligence. Not all AI problems are equally valuable for sustainability. Resources such as climate change AI, which maps high impact application to specific AI methods, and project drawdown, which identifies the most efficient and scalable climate solutions, provide critical guidance in making this decision. For DWaste, this means focusing on tangible climate goals, waste reduction, advancing the circular economy, and designing resource efficient systems. We continually ask the foundational questions to ensure net positive impact. Does this AI solve more climate problems than it creates? This mindset ensures our intelligence is not only powerful but also purposeful for the planet. The environmental impact of AI is real and growing, but building greener AI is possible through deliberate, responsible design. At DWaste, we demonstrate that it is feasible to create powerful AI applications with a significant lower carbon emission. Our blueprint follows a clear, actionable path: measure your carbon footprint, optimize your models, and infrastructure for efficiency, and deploy system wisely, prioritizing sustainable practices at every stage. This approach proves that AI and environmental stewardship can and must go hand in hand. This concludes our look at greener AI in action, the DWaste blueprint. We have demonstrated a crucial truth: a low carbon AI model is achievable. This blueprint applies that AI with purpose, a concrete plan for turning waste into insights and intention into impact. We invite you to join us in implementing this vision. Thank you.